Okay, on lesson 8.6, we're going to solve exponential and logarithmic equations. So there's two types, logarithmic and exponential, but we're going to have various methods. Now the first part says solve these by equating the exponents. The first thing you're going to have to do is rewrite the bases so that they are the same base. So when I look at my bases in number 1, we have a 4 and we have an 8. And you can tell that there's some things in common with those numbers, but if I want to break them down to their most common base, it's a common base of 2. So 4 is really a 2 squared. So I'll just write it like this for now, and it's taken to the 3x power. And 8 is really a 2 to the 3rd power. And then it's got an x plus 1 off to the other exponent. Now use your properties of exponents that says exponent on top of exponent, we are supposed to multiply these together. So this becomes 2 to the 6x. And then 2 to the, be careful, this is a distribution problem, 3x plus 3. Now since these are now the same base, the only way for these to be equal is for the exponents to be the same thing as well. So we're going to set up an equation that says 6x must be equal to 3x plus 3. So once you have your equation set up, you're just going to solve like you normally would. We're going to subtract the 3x and divide by 3, and you get x equals 1. So number 2, we have a base of 2 and a base of 32, and I think the common base in this case is also going to be a 2. So if I rewrite 32 as a 2, he's really 2 to the 5th power. And then he still has an x minus 1. So again, exponent property says power to a power, we're going to multiply these together. So we have 2 to the 4x is supposed to be equal to 2 to the 5x minus 5. Don't forget to distribute. And now that we have the same base, we can just set up an equation that says 4x should equal 5x minus 5. So I'm going to subtract 5x over here and get negative x equals negative 5. So x equals 5. Okay, number 3, we have an 8 and we have a 16. And think about it for a little bit, but their common base is going to be a 2 again. They're not always going to be a 2, we just happen to have a few 2's here. So 8 is really 2 to the 3rd, taken to the 5x, and 16 is really 2 to the 4th, taken to the 3x plus 4. So again, multiply your powers together, and don't forget to distribute over here. We've got 2 to the 15x equals 2 to the 12x plus 16. Since now the bases are the same, we can equate the exponents. 15x equals 12x plus 16. I'm going to subtract the 12. I feel like I messed up, but I think this is right. Divide by 3 on both sides, leave it as a fraction, 16/3. Okay, on number 4, I think 6 is going to be our common base because 216 can be written as 6 to the 3rd power. So if I go ahead and do that, this time there's no other exponent, so I think we're just ready to equate our exponents since now we have the same base. So 2x minus 7 has to equal a 3. I'm going to add the 7 to both sides and divide by 2. So x equals 5. Okay, a different technique for solving a problem is if we were to take a logarithm to each side. Now, the last section only worked if they had common bases. So when I look at number 5, there's no way I can write a 2 and a 7 to have a common base. And remember from the last lesson, the major property of logarithms says that if you have a logarithm in front of something with an exponent, the whole point of a logarithm is to bring the exponent down. Now remember, our calculator can only do 2 types of logarithms. We can only use a common logarithm, base 10, or a natural logarithm. Sometimes it doesn't matter what kind of logarithm you use, and sometimes it does. So let's look at number 5. Our base is a 2, so I don't think a common or a natural is going to be any better. And honest to goodness, I always choose natural because it's one less letter and I'm that lazy. So what I'm first going to do is I'm going to apply a natural log to the left side of the equation, and remember, whatever you do to the left, you have to do to the right. So the property of logarithm says that this exponent is going to come down in front of the problem. So we have x times the natural log of 2 equals the natural log of 7. Now the natural log of 2 and the natural log of 7 are just some gross decimal on your calculator. So if I wanted to solve for x times a number, I would just divide by whatever that number was. So if I divide both sides by the natural log of 2, and I type this in my calculator with parentheses exactly as shown, I'm going to type this on my personal calculator, you get 2.807. And that is your answer. Okay, number 6. We don't think we're ready to take a logarithm yet because it seems like we can do a little simplification here. For instance, we could subtract the 4. So you've got 10 to the 2x minus 3 power equals 17. And now I'm ready to take a logarithm so I can bring the exponent down. Now in this case, it would make a difference whether you chose log or natural log because our base is a 10. I think it would be really smart if we chose a common log, and I'll tell you why. Since common logs are base 10, these are just going to end up canceling out. So the 2x minus 3 drops down, but you still have common log of 17 over here. Now remember, common log of 17 is just something you can type on your calculator, 1.230. So we have 2x minus 3 equals 1.230, and then solve from there. So depending on how you round, add 3 and divide by 2, I think you get 2.115 roughly. So as you can tell, these answers are not going to be pretty, but the idea is you're always going to apply logarithms. Let's look at number 7. I think before we start taking logarithms, we should subtract the 3. So you've got e to the 2x equals 5. Now to get the exponent down, I must apply a logarithm, and because my base is an e, I think it would be very smart if we chose a natural log. Natural log and e are just going to cancel out because of the inverse property, and all that does is bring our 2x down. And the natural log of 5 is something that I'm going to type on my calculator, and it's 1.609. That's just something I typed. So when I divide that by 2, I get 0.805. Okay, number 8. There's nothing to simplify, so we're ready to take our logarithm. Because our base is a 2, it's not going to matter if you do common or natural. So whichever one you'd like to do, go ahead. Again, I always do natural when I am given a choice because I'm lazy and it's one less letter. So this exponent is going to come down in front. That's the property of logarithms. So when I bring the exponent down, I have to use parentheses because he's more than one term. And now we need to do a little simplifying on our calculator. So if I type the natural log of 2 on my calculator and then I type the natural log of 25 on my calculator, I can change these to their decimal components. So we have x plus 3, and then natural log of 2 is really a 3.22. No, it's not. It's a 0.693. You can write it behind or in front. She's got the binder. And natural log of 25 is 3.22. Now I could distribute the 0.69, that's supposed to be a 3, or I could just go ahead and divide by 0.693 right now. So we have x plus 3 equals 4.65. Well, 4.646 if I round to the right number of places. And then when I subtract 3, I get 1.646. So as you can see, when you can't use a nice pretty logarithm that'll cancel with one of your bases, the work gets a little trickier, a little grosser, and that's okay. Number 9, good news, we have a base e, so we're going to use a natural log because it's going to cancel. So natural log and e cancel, the x minus 4 drops down, and the natural log of 27 on my calculator is 3.296. I'm going to go ahead and add the 4 to both sides and get 7.296. Good news again on number 10. We've got a natural log idea because it's going to cancel with the e. So you have x plus 5. And then natural log of 125 would be a 4.828. And when you subtract the 5 from both sides, you get a negative 0.172. Good news again on number 11. Apply the natural log. It's going to cancel with your e. So on the left you just have a 3x minus 1. The natural log of 49 on my calculator is 3.892. So we're going to add 1 and then divide by 3. 1.631. Okay. Oh, kind of a lot of work to do here on number 12. First, we're going to have to subtract the 10. Can't apply the logarithm until your base is isolated. I'm going to write the x on the outside. Okay, we're going to go ahead and divide by 3, because again, we need to have the base isolated. Don't really need the parentheses. Now that we have our base isolated, we're going to apply a logarithm. Because our base is 1.5, it doesn't matter if we use a common or a natural. So I'm going to use a natural, just because I like it. And that's going to take the x and bring it down in front. So we have x times the natural log of 1.5 equals the natural log of 90. Now remember, the natural log of 1.5 and the natural log of 90 are just numbers on our calculator. So if I type that in, natural log of 1.5 is 0.405, so we have 0.405x. Natural log of 90 is it's going to round up to 4.5, and now we just solve. And we get 11.111. And again, depending on how you round, you might have a little different answer. Okay, we're going to use an exponential model now to use to do an application problem. We're cooking a licha, which is an Ethiopian stew. When you take it off the stove, its temperature is 212 degrees. That's boiling. The room temperature is 70 degrees. And the cooling rate is 0.046. How long will it take to cool the stew to serve to a serving temperature of 100 degrees? Now they give us a model that says t equals t sub naught minus t sub r times e to the negative rt power plus t sub r. And they're going to define for you what all these variables mean, but t is the serving temperature, t sub naught is the initial temperature, and t sub r is the room temperature, and of course r is the rate. So we just have to very carefully plug in what we know. So if I start with t, which is the serving temperature, we want that to be 100. So I'm going to put down 100 equals, parenthesis, t sub naught is our initial temperature, which was 212 when we took it off the stove. T sub r is room temperature, which is 70. E, now up in the exponent, we've got a negative. Our rate is 0.046, and then t is what we don't know, so we're going to leave that as a variable. And then plus t sub r, which remember was our room temperature, 70. So we're going to have to solve this, and it looks really gross, but it's not that bad. We're going to start by subtracting the 70. Whoops. We have 30 equals, I'm going to simplify this a little bit and get 142, 212 minus 70, and then e to the negative 0.046 t power. Again, we can't apply logarithms until we have the base isolated. So you're going to divide by 142. And you get a decimal, of course, 0.211 equals e to the negative 0.046 t. And now that our base is isolated, we're going to apply a logarithm. It would be smart if we applied a natural log. So natural log of 0.211 is negative 1.556. And then e and natural log are going to cancel, so you have negative 0.046t. And then your final step to solve for t is to divide by negative 0.046. And you get 33.8. I'm assuming that's minutes, but I'm sure they told me. So roughly 34 minutes. Our next section has us solving logarithmic equations, and these are actually really easy because it's a logarithm equals a logarithm. So what happens is this would only come out true if the inside of the logarithms were the same thing. So we're going to essentially ignore the logarithms. We're going to say 5x minus 1 is to equal x plus 7. So now we're just going to solve. So we're going to subtract the 1x over here and get 4x, and then add the 1 and get an 8. So you get x equals 2. Same thing here, we're essentially just going to ignore the natural logs. 6x plus 3 has to equal 2x plus 27. We're going to subtract the 2x, subtract the 3, and when we divide by 4, we get x equals 6. And then same thing here on number 3. We're going to ignore the logarithms and say x squared is supposed to equal 16. Now don't forget, when you square root, you end up with two possible answers, plus and minus 4. This technique is going to work when we have a logarithm equal something other than a logarithm, and it's called exponentiating, because exponents or exponential functions and logarithms are inverses of each other, so they're going to cancel each other out. So what you do is you identify what is the base of my logarithm. When I look at number 6, the base of your logarithm is a 5. So what we're going to do is take a 5 and kind of shove it up underneath the problem. So right here you've got 5 to the log base 5, but they're going to cancel out and give you 3x plus 1. But over here you have 5 squared, and 5 squared is really a 25. And now you just have a nice linear equation to solve, and you get x equals 8. Okay, same thing on 7, except before we start number 7, we have to isolate the logarithm. So you're going to divide by 12 on both sides and get a decimal. So you've got the natural log of x equals 3.667. Now the base of a natural log, remember, is an e, we just don't write it. So when I exponentiate this problem, the base I'm going to use is an e. So on your calculator, you're going to have to type in e to the 3.667 power. And you get 39.134.